Hello everybody and welcome to Gravitational Fields Lesson 7. Now in the last video, just to remind you, we looked at three key ideas. Firstly, equipotentials, and equipotentials are lines of equal potential. We then looked at the potential gradient and we derived the equation G is equal to minus delta V by delta R. So G, of course, being the gravitational field strength, and minus delta V by delta R, well, that's just the gradient, or at least the delta V by delta R bit, is just the gradient of the V against R graph. After that, we defined gravitational potential energy, and of course we used the original definition of potential, which was work done per unit mass, and we rearrange that, just say delta W is equal to m delta V, and from that we derive the equation potential energy is minus G big M little m over R. Now, as far as the gravitational fields topic and series of videos goes, we've done all of the major ideas that we need to cover. We're going to take this video and the next video in order just to work through a couple of little bits and bobs that go along with the gravitational fields topic, really just to round everything off, to use the cliche, to dot the I's and cross the T's, and just make sure that we know everything and we've studied everything that we need to worry about with gravitational fields. Firstly, for this video then, we're going to have a look at what happens to the gravitational field strength when we're inside a body, so when we're inside the planet, when we're inside a star or something like that. Now we know that outside a planet, outside a body, that the equation is minus gm over r squared, and therefore, as we've seen before, it is an inverse square law. Now, of course, when we're outside the body, it doesn't matter how far away we are from the surface. We've always got the same amount of mass between us and the centre of mass of the object. Now, of course, this question goes back to the age-old problem of, if you could drill all the way through down to the core or all the way out to the other side of the Earth, what would happen? And it's almost an extension of that thought process. Now, in order to have a look at what happens inside, what I want you to do first is imagine that there is us stood on the surface of the Earth. And we have to ask ourselves, well, what is it that is pulling us down towards the centre? Well, the answer, very simply, is all of the mass that is between us and the centre of mass of the body, the centre of mass of the planet. Now, when we go inside the planet, so let's say that we were able to drill that hole all the way through and to the other side, and let's say that we got to a point there, well, we're still being pulled down towards the centre of mass of the Earth. But now, rather than the entire mass of the body pulling us down towards the centre of mass of the Earth, what we're left with is the mass of whatever is in between us and that centre of mass. So we're just left with the mass of that dotted blue. I know it's a circle, but obviously what you need to do is you need to imagine that therefore in 3 dimensions is a sphere. Now, of course, you may be thinking to yourself, well, what happens to all of the other stuff? What happens to everything that's outside that blue dotted line? Well, any forces that are acting on us when we go down into the Earth like that, any forces from all of the other bits that are outside that blue dotted line end up cancelling each other out. So we end up with no net force and no, therefore, net gravitational field strength acting from all of the stuff outside. All we're left with is whatever is between us and the centre of mass. Now obviously we've got the distance there, which would be r. Okay, which will be that distance there. Now, in order to see what happens next, we're going to make one key assumption. We're going to assume that the body has a uniform density. Okay? In other words, the density of all the material that's at the surface of the planet is the same as the density that's at the core. Now, I know full well that that's not necessarily a true representation of what's going on, and I will in a moment show you how this really works, but just for the purposes of what we're doing, we're going to assume that we've got a uniform density. Now, of course, we know the density equation. The basic density equation is rho is equal to m over v. It's the mass per unit volume. Now, when we rearrange that for mass, we see that mass is density multiplied by volume. What we're interested in then is the mass, as we said, of whatever is inside us. It's the mass of that blue shaded area there. Well, how do we work out the mass of just that blue shaded area? Well, coming back to it, we know that that blue shaded area is a sphere with a radius r, and therefore we can work out its volume very easily. The volume of a sphere is given by 4/3 pi r cubed. Substituting that in then, we see that mass is, well, here comes our volume, here comes the substitution, 4/3 pi r cubed multiplied by rho, the density of the planet. The next stage of this idea then is to take this equation for mass that we've just derived and to substitute it in to the gravitational field strength equation. So let's do just that. So G is equal to minus, well, we've still obviously got the G over r squared bit, and we're going to multiply that by our substituted value, which is 4/3 pi r cubed times rho. Now when we tidy all of that up, we're going to end up with the following: minus 4, I'll just put the 4 over 3 in there so we can see where that 3's gone as well. We've still got the G, obviously we've got pi r cubed and rho, and on the bottom we've still got the original r squared, which I'm going to draw there just to show you that we've got r appearing in some way, shape or form on both the top and the bottom of this equation. Finally then, for the algebra side of things, again we can see that on the top we've got r cubed and on the bottom we've got r squared. The r squared will therefore cancel with at least 2 of those r's in the r cubed, and what we're left with then is that the gravitational field strength inside the planet is minus 4/3 G pi rho times r. Now obviously that's the equation. We need to now gain a little bit of understanding from it. When we look at this equation, everything that we've got here, the minus 4/3 G pi and rho, these are all constants. And therefore what we're left with is that the gravitational field strength is proportional to the distance from the centre of the planet. And you can see that there's no other indices appearing here. It's just nice and simply G is proportional to R, and therefore we have a linear relationship. Now then, we'll attempt to draw the graph of G as a function of distance from the centre of mass. So here is the distance, and on the vertical axis we're going to do the modulus of G, just to make sure that we're keeping everything positive, just to make life easy for us for now. Now, as the first reference point, we know that we've got the radius of the body, radius of the planet, whatever we're looking at, and we'll call GS the gravitational field strength at the surface. So we've got our first reference point, which will be that point just there, nice and easy. Outside the planet then, which is everything in this direction, the graph is an inverse square graph. Because we know that G is proportional to 1 over r squared. And then inside the body we have a straight line because, as we said on the last slide, that the gravitational field strength was directly proportional to the distance. Now, of course, as I said before, that assumption that we've got a constant density inside the Earth, we know full well isn't right. It's a model. It doesn't necessarily work out exactly like that. We know full well that the core of the Earth is far denser than the mantle above it. So what you can see on the screen then is a more accurate representation. You can see that you've got the sort of longer green dashed line, which is here on the graph, which shows us the constant density that we assumed. Obviously you've got the blue line outside, which shows you that inverse square bit. So here is the inverse square. And you can see that there are two other models suggested. Firstly, in the finer dotted green line is what they refer to as linear density. So in other words, the density is a linear relationship with the distance as well. And then the solid blue line is a more representative idea of how it would really work. You can see that's labelled PREM, which is the preliminary reference Earth model, which is a model that a lot of geologists and geophysicists use in order to really understand what's going on inside the Earth. So, okay, we can assume density is a constant. It's a model, but it's not necessarily the most accurate model that we can come up with. But like I said, that's at least good enough for our purposes at A level at the moment. Moving on to the second part of this lesson then, we're going to define and obviously explore escape velocity. Now you can see the definition on the screen there. So the escape velocity is the minimum velocity required for an object to escape completely from a gravitational field. Now what we mean by to escape completely is that we need to get to a point where there is no longer a force experienced by an object due to a gravitational field. Now, of course, if we go back to when we first defined gravitational potential, the only point where that is relevant and that is applicable is when we are an infinite distance away. And of course, if we bring back the original definition that we did in previous videos of gravitational potential is the work done per unit mass in moving it from infinity to that point. Now what we're doing is the exact opposite. We're moving it from a point, and here we're saying it's from the surface of a body, surface of a planet, surface of whatever we're looking at, out to infinity. Therefore, we can say that the change in potential in doing that will be positive gm over r. Now really all we're going to do now is just going to tie a few different things from previous ideas and previous videos together. In order to calculate velocity, we're first going to calculate or derive the kinetic energy, which is of course a half mv squared. Now, in order to completely escape the gravitational field, that must therefore be greater than or equal to the potential energy at the surface. And of course, the potential energy at the surface we can determine, we can calculate by just doing the mass multiplied by the change in potential. So you can now see that we're starting to put an equation together, or actually it's an inequality if we're being more accurate with this. And we're saying therefore that the half mv squared, the kinetic energy, must be greater or equal to the mass multiplied by the change in potential. Now at this point you'll see that the masses cancel out, and what that implies to us is of course that the mass is irrelevant. In other words, the escape velocity, at least theoretically, for an electron would be exactly the same as the escape velocity for a space shuttle or something like that. Let's now finish off this derivation. So half v squared must be greater than or equal to gm over r. Multiply both sides by 2, v squared must be greater than or equal to 2gm over r, and therefore the escape velocity must be greater than or equal to the square root of 2gm over r. Now I know I've square rooted there, and we should of course in theory get plus or minus, but of course the sort of negative value of velocity doesn't really mean too much to us in this context. So there you have the equation for escape velocity. Okay, and here just to remind you, r is the radius of whatever body we're trying to escape from, of course assuming that we are going from the surface. So here is your question then for this video. Calculate the escape velocity of the Earth and the Sun. As usual, pause the video, go away and calculate your answers, and then come back and resume the video when you think you're there. So this one is relatively easy then. We've already got the equation, we've got the escape velocity is greater than or equal to root of 2gm over r. Now obviously m here will be the mass of either the Sun or the Earth respectively, and the same with r will be the radius of those bodies. So if we do the Earth first, v has got to be greater than or equal to root of 2 times 6.67 times 10 to the minus 11 multiplied by the mass of the Earth, which is 5.98 times 10 to the 24 kilograms, and that is going to be divided by the radius of the Earth, which is 6,370 kilometres, 6.37 times 10 to the 6 metres. Now once you plug all that in and maybe do a little bit of tweaking with the SI prefixes, the way that I would write that would be 11.2 kilometres per second. For the Sun then, v is greater than or equal to root Same again, 2g, so 2 times 6.67 times 10 to the minus 11, multiplied by the mass of the sun now, so 1.99 times 10 to the 30, and that will be divided by the radius of the sun, which is 6.96 times 10 to the 8 metres. And again, once we've plugged that into the calculator, done all our rounding and a little bit of converting into SI prefixes, we end up with the escape velocity of the sun being 618 kilometres per second. So to summarise this video then, we've looked at two key things in this one. Firstly, we've looked at the gravitational field strength inside a body, whether that be a planet or the sun or anything like that. And we said that if we draw a graph of distance from the centre of mass against the modulus of the gravitational field strength, that inside the body we will have a linear relationship, whereas as soon as you got to the surface and we're going out from there, it will be an inverse square relationship. Secondly then, we looked at escape velocity, and we got the definition of escape velocity as the minimum velocity required for an object to escape completely from a gravitational field, where the escape velocity is therefore greater than or equal to 2gm over r. So that's it for this video. Again, thank you for watching. If you've got any questions, let me know, and I'll see you in the next video.